Open with the chilling fact: two brand new aircraft, same model, same manufacturer, crashed within 5 months, claiming 346 lives. This wasn't a freak accident, it revealed a systemic failure that shook the aviation industry to its core. We're talking about the Boeing 737 MAX, a plane heralded as the future, yet grounded for nearly 2 years. The official narrative often focuses on a software glitch, but our deep dive reveals a more complex, interwoven tapestry of corporate decisions, regulatory oversight, and engineering compromises that ultimately led to tragedy. The 737 MAX was Boeing's answer to the highly successful Airbus A320neo. Facing immense market pressure, Boeing rushed the MAX into development, aiming for a cost-effective upgrade that could use existing 737 pilot certifications. This meant minimizing changes to the airframe and cockpit. The core idea was to make it feel like just another 737 to pilots, reducing the need for expensive and time-consuming simulator training. This commercial imperative, while understandable, laid the groundwork for future issues, prioritizing speed to market over critical re-evaluation. After Lion Air Flight 610 crashed off Indonesia in October 2018, initial investigations pointed towards a control issue. But when Ethiopian Airlines Flight 302 met a similar fate 5 months later in March 2019, the similarities were stark. Both planes experienced erratic flight paths, with the nose repeatedly pitching down before impact. It became undeniably clear that a common, critical factor was at play. Global aviation authorities, initially hesitant, quickly recognized the pattern's grave implications, leading to an unprecedented global reassessment. The crucial common factor was a new automated flight control system called MCAS, or Maneuvering Characteristics Augmentation System. Introduced specifically for the 737 MAX, MCAS was designed to automatically push the aircraft's nose down under certain conditions, primarily to compensate for the MAX's larger, more forward-mounted engines. These engines altered the plane's aerodynamic characteristics, giving it a tendency to pitch up during high angle of attack maneuvers. MCAS was intended to make the MAX handle like earlier 737 models, maintaining flight stability. The fatal flaw in MCAS lay in its design: it relied on input from only one of the aircraft's two angle of attack, or AOA, sensors. If this single sensor malfunctioned and sent erroneous data, MCAS would activate repeatedly, forcing the aircraft's nose down, even if the plane was not actually at a high angle of attack. There was no redundancy, no cross-referencing with the second sensor, and critically, pilots were not adequately informed about its existence or its potential for runaway activation, making it a critical single point of failure. Flight data from Lion Air 610 revealed a terrifying struggle. The aircraft's faulty AOA sensor sent incorrect data, indicating a stall, which triggered MCAS. Over the course of the 11-minute flight, MCAS engaged over 24 times, forcing the nose down. The pilots fought valiantly, attempting to counter the system, but without full knowledge of MCAS or its activation parameters, they were overwhelmed. This initial tragedy, costing 189 lives, should have been an immediate alarm for the entire aviation ecosystem, highlighting critical design flaws. Just 5 months later, Ethiopian Airlines Flight 302 presented an almost identical pattern. Soon after takeoff, its faulty AOA sensor also began feeding erroneous data to MCAS. The system again commanded the nose down repeatedly, locking the pilots into a desperate and ultimately futile struggle. The black box recordings depicted a similar, escalating battle against an automated system they couldn't fully comprehend or disable effectively. The loss of all 157 people on board solidified the global consensus: this was no coincidence, but a systemic and dangerous failure repeating itself. A critical failure point was the lack of pilot awareness and training regarding MCAS. Boeing intentionally downplayed the system's role, fearing that extensive pilot training on a new system would delay certification and add costs for airlines. Pilots transitioning to the MAX received only minimal computer-based training, which did not fully explain MCAS or its potential for runaway activation. They were essentially flying a new, complex system without being fully equipped to understand or counteract its most dangerous failure modes, a fundamental breach of operational safety. Boeing was under immense commercial pressure. Airbus had launched its A320neo, a more fuel-efficient version of its popular single-aisle jet, and was quickly racking up orders. Boeing needed a swift, cost-effective competitor. The decision to base the MAX heavily on the existing 737 airframe, using larger engines, created the aerodynamic need for MCAS. This rapid development cycle, driven by market urgency, arguably prioritized speed and cost over thorough design scrutiny and comprehensive safety protocols, a critical trade-off that proved disastrous. The push for efficiency wasn't just about market share, it was also about maximizing profit margins. Boeing's strategy involved minimizing design changes that would require new pilot certifications, which meant avoiding costly simulator training. Instead, a cheaper, iPad-based training was offered. This pursuit of cost reduction appears to have extended to critical design choices, such as relying on a single AOA sensor for MCAS, instead of implementing a more robust, redundant system that would have been significantly more expensive to develop and integrate. Historically, Boeing was an engineering-first company, renowned for its technical prowess. However, a significant cultural shift occurred after its merger with McDonnell Douglas in the late 1990s. The focus increasingly moved from engineering excellence and safety leadership towards shareholder value and financial metrics. This shift arguably led to a diminished voice for engineers, creating an environment where cost-cutting and aggressive timelines sometimes overshadowed rigorous safety testing and design redundancy, fundamentally altering the company's core values. The Federal Aviation Administration, or FAA, is responsible for certifying aircraft in the U.S. However, for the 737 MAX, the FAA delegated a substantial portion of the certification process back to Boeing itself through its Organization Designation Authorization Program. This meant Boeing employees, often under immense internal pressure, were effectively certifying their own work. This self-certification model led to critical components like MCAS receiving insufficient independent scrutiny, creating a regulatory blind spot that proved disastrous and eroded public trust in oversight. The certification process for the 737 MAX was marked by a series of compromises. The FAA's delegation of authority meant that critical changes, like the MCAS system, were not reviewed with the depth they warranted. Boeing also reportedly withheld information about the system's full capabilities and its potential for repeated, uncommanded nose-down inputs. This lack of transparency, coupled with the FAA's reliance on Boeing's internal assessments, accelerated the approval process at the expense of comprehensive safety verification, putting profits over people. Distressing reports later surfaced from Boeing employees who had raised concerns internally about the 737 MAX development and certification. These whistleblowers described an environment where warnings were downplayed or ignored, and where aggressive deadlines overshadowed safety concerns. One engineer testified that he felt pressured to go faster and that the design and test processes were rushed. This internal dissent, tragically unaddressed, underscores a severe organizational breakdown within Boeing, where critical safety voices were systematically silenced. Following the Ethiopian Airlines crash, global regulators, beginning with China and Europe, quickly grounded the entire 737 MAX fleet. The FAA, initially slower, eventually followed suit. This unprecedented grounding of a new aircraft type had massive economic consequences for Boeing, costing billions in lost revenue, compensation to airlines, and production halts. Over 400 aircraft were delivered but couldn't fly, and thousands more orders were impacted, causing immense disruption across the entire aviation supply chain and to global travel plans. To get the 737 MAX back in the air, Boeing undertook a comprehensive software overhaul. The MCAS system was redesigned to take input from both AOA sensors, cross-referencing data and limiting its activation to a single instance per event. Crucially, pilots now had the ability to override it more easily. This technical fix, combined with mandatory simulator training for pilots and a rigorous recertification process by global aviation authorities, aimed to address the immediate technical vulnerabilities that led to the crashes and restore confidence in the aircraft. The crisis forced a deep introspection within Boeing. The company replaced its CEO, faced multiple investigations, and paid significant fines. The focus shifted back, at least rhetorically, to engineering safety. Rebuilding trust with regulators, airlines, and the flying public became paramount. This isn't merely a technical challenge, it's a fundamental test of corporate integrity and culture. The lingering question remains: can a company so deeply entangled in commercial pressures truly recenter its values around uncompromised safety, or will commercial imperatives always loom large? The 737 MAX tragedies have fundamentally reshaped aviation safety and regulatory oversight. Regulators globally are scrutinizing certification processes more thoroughly, reducing reliance on manufacturer self-certification. The balance between innovation, speed to market, and absolute safety is being re-evaluated. This crisis serves as a stark reminder that even with advanced technology, human decisions, corporate culture, and regulatory rigor remain the ultimate arbiters of airworthiness. The lessons learned, though tragic, are vital for preventing future catastrophes and ensuring public confidence in air travel. In conclusion, the real reason Boeing's 737 MAX crashed twice isn't just a software bug, it's a complex confluence of factors: a flawed automated system, inadequate pilot training, intense commercial pressure, cost-cutting imperatives, a shifting corporate culture, and insufficient regulatory oversight. Each factor, on its own, might have been manageable, but their combined effect created a perfect storm. The tragedies underscore that safety in aviation is a multi-layered responsibility, demanding unwavering vigilance from designers, manufacturers, and regulators alike, to prevent such a catastrophic sequence from ever occurring again.